Why did bitmap have 1 for product underscore sk equal 31? I don't see a corresponding index. Let's correct this first because this is the root of confusion. Rule, non-negotiable. Every bitmap has exactly 1 bit per row position. Bit position k equal row k. There's no lookup by value index. There's no matching by key. Only position. So you actually get this by bitmap. So you count how many times that occur in that column. Example again slowly. Row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Product underscore sk 69, 69, 74, 31, 31, 29, 30, 30, 31, 68. Now evaluate product underscore sk equal 31. Row 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Comparison n, 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 y, y, n, 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 y, n. Bitmap 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. Those ones do not mean index 31. They mean at row positions 3, 4, and 8, the value is 31. This is the single most important idea in column stores. If both bits are 1, is that returned to the business analyst? Yes, but not as bits. What the analyst writes, select count asterisk from sales where product underscore sk equal 31 and store underscore sk equal to 3. What the engine does, builds bitmap A to product underscore sk equal 31. Second, build bitmaps B to store underscore sk equal to 3. Third, computes A and B. Fourth, count ones. What the analyst sees, count result 124,918. They never see bitmaps, they see aggregates, charts, tables. Third, how does this look in real life? Real business question, how many times was product 31 sold in store 3 last month? SQL, select count asterisk from sales where product underscore sk equal 31 and store underscore sk equal to 3 and date is greater than or equal 2025-01-01 and date less than 2025-02-01 semicolon. Column store execution, load bitmap, product equal 31 and bitmap, store equal to 3 and bitmap, date to range, then count bits. No rows reconstructed, no joins yet. CPU does vector math. So it does this using its ALU. And since it's vectorized and it's just bitmap, it's in endwise, it's actually fast. That's why dashboard feels instant. If vertical sort, does it become O log n? Important correction, no. Bitmap scans are still ON, but they are sequential, vectorized, cache friendly, so you don't need a random branch prediction or a reset of a cache on your multi-core CPU, and it often skips huge ranges because you choose the column. Sorting helps because matching values become contiguous. Bitmaps compress into runs. CPU can skip blocks. So it's not binary search. It's faster linear scan. So it's just faster than ON, but it's not a binary or O log n. Sorting helps because matching values become contiguous. Bitmaps compress into runs. So instead of having branch instruction that jump into lines, you get a contiguous memory. And bitmaps compress into runs, the run encode length encoding. So that's actually just a bit Instead of keeping all the numbers, you just keep how many times that occurred in that row. So think highway with cruise control versus zigzag city walking. When it loads compressed bitmap, how is it compressed? Not like LSM, gzip, or ZSTD. Column store use semantic compression. Example bitmap 100000011110000000111. Run length encoding, it sees 60417031. So it's easier load to the register of the CPU because you compress it like this instead of those huge binaries. That's what the book shows 5 comma 4 comma 3 comma 3. Why is this powerful? Compression understands data meaning. So the meaning of this binary, it understands that instead of putting all the binary. Therefore, it's also better in cache because it's compressed. It's also better in a CPU pipeline because it can execute more with less time. And CPU operates directly on compressed runs. No decompression needed. So a CPU also operates directly on compressed run because it's vectorized. It just need to run its arithmetic that is mapped to its instruction set. No decompression needed. LSM compression, generic byte compression, needs decompression before use. So for LSM, you actually need to decompress. Here you don't need to decompress because CPU inherently support this. What do cache line jumps mean? This is inside the machine, not three easy pieces. Cache line, 64 bytes. CPU loads memory in blocks, not scalars. So it's kind of like how the memory load code streams and data streams to CPU registers. So the CPU constantly want to execute something, but if the memory stalls or the cache lines do not have that capacity, it won't be able to load. The memory won't be able to load that code in data storage. And CPU loads memory in blocks, not scalar. Row store problem, row to pointer to heap to pointer to column to pointer to next row. So it has a lot of branch instruction of jumping, and its data structure is node based, so it's jumbled. But it's different in column storage because it's contiguous. CPU constantly jumps memory. Cache misses. So since it's constantly jumps memory, you have a cache misses. Why? Because those that if you have that in contiguous loop, spatial locality means also a cache locality, or it will be available in cache better. So column storage advantage, with column array you have a contiguous data. CPU streams sequential memory, fewer cache misses, SIMD instructions, prefetching works. Book reference inside the machine, chapter on memory hierarchy, cache lines, instruction pipelines, SIMD/vector units. Diagram, row versus column versus LSM, row store OLTP. So we have row 1, row 2, row 3, product, comma, store, comma, price, then product, comma, store, comma, price, then product, comma, store, comma, price. Fast point lookup, bad for scans. Column store analytics. So you have a product 31 comma 31 comma 30 comma 69 comma 68 dot dot dot, next line store colon 3 comma 1 comma 3 comma 3 comma 3. Next line price 10, 20, 30, 40, 50. Scan columns, bitmaps, CPU optimize. LSM3 KV/Firestore like. So we have mem table to SS table sorted to SS table to compaction. This is right optimized read via indexes. How join works with bitmaps. This is beautiful. Select count next line from sales as next line join stores street s or st on s dot store underscore sk equal st dot store underscore sk next line where st dot region equal quote us next line end s dot product underscore sk equal 31 semicolon. Execution of this first bitmap for stores dot region equal quote us second map store ids to bitmap of store underscore sk third bitmap for product underscore sk equal 31 fourth and them still no rows joins become bitmap propagation. How BigQuery executes this? BigQuery columnar, Dremel engine, bitmap-like filters, massive parallelism, execution plan, push predicates down, first push predicates down, second read only needed columns, third apply vectorized filters, fourth aggregate locally, fifth shuffle partial results, sixth final aggregation. This is why BigQuery scans terabytes in seconds. Final mental model, lock this in. Row store is equal to follow pointers to find data. Column store equal mark positions, then operate on marks. Your confusion came from assuming rows must exist physically, values must match to join, indexes points to data. Column stores break all three assumptions. First, what build bitmap product underscore sk equal 31 actually means. There are two possible cases in a real column store. Case A, bitmap index already exists, most warehouses. This is the normal case for columns like product underscore sk, comma, store underscore sk. On disk, product underscore sk column, colon next line, dictionary 29, 30, 31, 68, 69, dot. Next line bitmap index, colon, next line value 29 to bitmap file. Next line value 30 to bitmap file. Next line value 31 to bitmap file. So no scanning is needed. Execution. Bitmap A equals to load underscore bitmap. Uh, argument code product underscore sk comma 31 next line bitmap B equal load underscore bitmap. Argument store underscore sk code store underscore sk comma 3 closing parenthesis next line bitmap C equal bitmap A and bitmap B next line count underscore ones argument bitmap C. That's it. This is why analytics queries feel magical. Case B, no bitmap index exists, fallback. Then the engine builds it on the fly like this. For I equals to 0, semicolon I less than num underscore row, semicolon I plus plus, open semicurly bracket, next line bitmap argument I equal column, argument I equal 31, semicolon, closing parenthesis. This looks simple because it is simple, but the power is how it runs, SIMD, cache compression. Second, how this differs from LSM, key mental switch, LSM3, firestore style, lookup, argument key, next line check, mem table, next line check SS tables, newest to oldest, next line follow index pointers, next line read blocks. LSM answers, what is this? What is the value for this key? Column store answers, which row position satisfy this condition? No pointers, no chasing, no version resolution. It produces a Boolean vector. That's why it feels alien. It's not map lookup, it's set algebra. Third, what bitmaps compress into runs really means. Like Let's make this painfully concrete. So we have this binary 00111011. That's 46 bits, 46 rows. In rand length encoding, you wouldn't see that binary. You would only see 10 0 at first, 11 ones, then 12 zeros, 7 ones, literally stored as 10 comma 0 for the first array, comma 13 comma 1, second array, comma 12 comma 0, third array, fourth 7 comma 1. Instead of 46 bits, 8 integers. Why this understands data meaning? Because column is sorted or clustered. Same value appears together. Condition produce long stretches of zeros or 1. This is semantic compression, not gzip. LSM compression, blind byte patterns. Bitmap compression compresses logical truth values. Fourth, how AND/OR works on compressed bitmaps. Here's the part most people never explain. Bitmap E, product equal 31. So we have first array 10 comma 0, comma second array 13 comma 1, comma third array 12 comma 0, comma fourth array 7 comma 1. Bitmap B, store equals to 3. So first array 5 comma 0, comma second array 8 comma 1, comma third array 29 comma 0, comma fourth array 4 comma 1. And operation, align runs and values, emit result runs. This happen without expanding bits. Pseudocode while argument run A and run B, semi-curly bracket, next line len equal mean, argument run A dot length, comma run B dot length, semicolon, next line out underscore bit equal run A dot bit and run B dot bit, semicolon, next line emit, argument len, comma out underscore bit, semicolon, next line advance shorter range, semicolon, next line closing semi-curly bracket. This is why it's insanely fast. Where caching happens, 3 levels. First, OS page cache. Bitmap files live in memory once touched. So the bitmap files live in memory once touched. So that's the OS page cache. Second, column store buffer full. Hot bitmaps pinned in RAM. Third, CPU cache L1, L2, and L3. And operation stream sequential memory. Prefetch works perfectly. No random access equal no cache misses. So since we don't have this random data structure like node, we don't have this random access here. SIMD, how CPU actually executes this. This is the inside the machine territory. Instead of 4, I equals to 0, semicolon I less than n, semicolon I plus plus. The next line out, argument I equals to A, argument I and B, argument I, semicolon. CPU does and 256 bits at once. Example, AVX2 equal to 56 bits equal to 56 row per instruction. AVX-512 equal 512 rows per instruction. That's why 1 billion rows can be filtered in milliseconds. LSM trees cannot do this because they follow pointers. Exact analogy to your LSM shell script. You had this grep code $1 database vertical line tail dash n1. That answer give me the latest value for this key. Column store equivalent AWK $2 equal 31 and 3 and $3 equal 3 count plus data but implemented as bit vectors, SIMD, RLE, no text parsing, no branching, same logic, radically different execution model. Firestore to BigQuery mapping exact. Firestore, you have documents colon, open semi-curly bracket, product underscore SK, comma store underscore SK, comma price, comma timestamp, closing semi-curly bracket. This store road-oriented index by primary key, secondary index via B3-like structures, good for OLTP. BigQuery export, we have product underscore SK column to bitmap index, store underscore SK column to bitmap index, timestamp column to range filters. Analytics query, select con asterisk, next line from firestore underscore export dot sales, next line where product underscore sk equal 31, next line end store underscore xsk equal to 3, becomes bitmap argument product equal 31, next line end bitmap store equal to 3, next line count. No documents are constructed. LiveKit Analytics real example question: how many screen shares happened in room X last week? Event table, we have room underscore ID, vertical line event underscore type, vertical line times type, vertical line or user underscore row. So each vertical is a column. Bitmap filters, we have bitmap argument room underscore ID equals to X, next line end bitmap argument event underscore type equal code screen underscore share underscore start, next line end bitmap timestamp in range. That's it. That's why analytics backends are separate from LiveKit's real-time path. Why this felt impossible to see? Because LSM3 control flow visible, column store data flow visible, LSM3 pointer base, column store position base, LSM3 branch heavy, column store branch free, LSM3 lookup mindset, column store set algebra mindset. You were trying to trace instructions, but column stores are about vector math. Final lock-in sentence, LSM3's answer what value belongs to this key. Column store answer which row satisfy this condition. Once you internalize that, bitmap indexes stop being abstract, they become inevitable.